So by now, you should have a good idea of how to compute uncertainties of sums, as well as you should understand the general way to compute uncertainty of a function. In this video, your objectives will be to know how to compute uncertainties of products and quotients, and then using the method for the general function, it's relatively straightforward to apply that to a combination of sums, products, and quotients. So let's start off with an example. And in this first example, this is just a very simple mixing problem. So we're going to have two solutions. The first one, let's say, has a mass sub A, and the second one has a mass denoted by m sub B. And then let's say that A and B are concentrations of a compound in each solution. So if we mix the two, we would get a final concentration C, and that final concentration is simply described by the mass of the first solution divided by the total mixture, the mass of the total mixture, times the concentration of the first solution, plus the mass of the second solution divided by the total mass, times the concentration of the second solution. And so let's also say that we know the concentration of A, we might measure it to have a value of A sub 0, but there's an uncertainty of that concentration of delta A, and likewise the concentration of B is measured to be B sub 0, and it has an uncertainty of delta B. So what is the concentration of the mixture as well as its uncertainty? Well, the uncertainty of C squared, again, is equal to the partial derivative of C with respect to the first variable, A, times the uncertainty of A, and that's squared, plus the uncertainty of the sum with respect to B, times the uncertainty of B, and that whole thing is squared. And therefore, the square of the uncertainty, which in this case might be the variance, is then m sub A over the total mass times delta A squared plus the mass fraction of the second solution times the uncertainty of the concentration of the second solution, delta B squared. And so therefore we would know how to compute C as being equal to C0 plus the square root of all of this. And of course C0 is equal to m sub A, ma plus mb times A0, the measured value, plus the mass fraction of solution B times the measured value of B. Okay? All right, let's move on to products. So here we'll describe the product as P being a product of a variable x times a variable y. And of course, that will be, well, x has a measured value plus an uncertainty, and y has a measured value, plus and minus an uncertainty. And I'm just remembering I should go back to my last example, and we describe A as having its measured value plus and minus the uncertainty. So I need to add plus and minuses to all this, right? So, so C will equal the measured value, which is this, times the square root of its variance. Okay, plus and minus the square root of its variance. Okay, now back to the product. So again, we know that the variance, or the square of the uncertainty of P, is equal to the partial derivative of P with respect to x squared, which becomes y, which is y naught plus and minus delta y, times delta x squared plus the partial derivative of P with respect to y, which is just x, times delta y squared. So you'll see here that we'll have a product of the measured value times a delta, this should all be squared, and this should all be squared. And so you'll see we'll have measured values times, in this case, y naught times delta x squared. But if we assume that the uncertainty in y is small compared to y naught, then any product of uncertainties, in this case y times delta x squared, will be a lot smaller. So let's do that. We'll assume that the uncertainties are smaller than the measured values, and we'll throw out products of uncertainties. And when we do that, we get that the uncertainty of P is equal to the square root of y naught squared delta x squared plus x naught squared times delta y squared. And it becomes convenient in this case to write the uncertainty in P in terms of the fractional uncertainty. Or delta P divided by P naught is equal to, well, let's write that as being squared, is equal to y naught squared over delta x squared divided by P naught, which is divided by P naught squared, which is y naught squared x naught squared, plus the second term, and you can see that these terms cancel, and we're left with delta x squared over x naught squared plus delta y squared over y naught squared. So we would give the answer of the product as P being equal to the measured value plus and minus the uncertainty, which is the square root of this. And so that becomes the square root of delta x squared over x naught squared plus delta y squared over y naught squared. So let's revisit our mixing example. And here, let's write the mass fraction of solution A as F, and that will be equal to m sub A plus the mass of the mixture of our two solutions, which would be mass A plus mass B. And we'll write out our mixing equation in terms of mass fractions as C is equal to the mass fraction of A times the concentration of solution A plus the mass fraction of B plus the concentration of solution B. So now, in addition to A and B being uncertain, let's say that the mass fractions are uncertain. So FA is equal to an estimated or measured value plus and minus an uncertainty, and likewise FB is a measured or a most likely value plus and minus its uncertainty. So we would proceed as writing the square of the uncertainty of C, or the variance, as being again equal to the partial of C with respect to F sub A times delta FA squared plus the partial of C as it changes with respect to the mass concentration of B times its uncertainty, and then to take into account the uncertainties of A and B, we proceed as before. And I'm forgetting to square these. We've got to square each of these. So the partial of C with respect to FA would be A, but again, we're going to do as we did before and keep only linear terms, so it becomes A naught times delta FA squared. And likewise, the partial of C with respect to B becomes B sub 0, delta FB squared. And then the last two terms describe the variance of C due to variation to uncertainty in A and B. So the partial of C with respect to A becomes FA, but again, we're going to keep only linear terms. We'll keep the most likely or measured value, and we'll do the same for this last term. And so this is how we would compute the variance of C in which all four variables are uncertain. So now let's consider a quotient. Let's look at how to take the uncertainty, compute the uncertainty of a quotient. So the quotient is, we'll refer to the general quotient as Q, and it's the quotient of X and Y, which again are themselves uncertain. So the squared uncertainty of Q is again equal to the partial of Q with respect to x times delta x, and that's all squared, plus the partial of Q with respect to y times delta y, and that whole thing is squared. So writing out the first term, the partial derivative of Q with respect to x is 1 over y, and we're just going to use y naught because, again, we're going to toss out any nonlinear terms of uncertainties. And then the second term, the partial derivative of Q with respect to y, is minus x naught over y naught squared. Again, throwing out any uncertainties, the uncertainties of x and y for that term, times delta y squared. And let's, again, like we did for the product, we'll describe this in terms of a fractional uncertainty. So we're going to write the Q naught squared as x naught squared over y naught squared. So the first term becomes delta x squared all over x naught squared. The two y naught squareds cancel for that term, and the second term becomes delta y squared all over y naught squared. Or I should show you how I got there. So we have a x naught over y naught to the fourth. That's from this term here. And we're dividing that by x squared over y naught squared. And so the x0 squared, those cancel, and then the y squared cancels, leaving only a 1 over y naught squared. And so the uncertainty, the fractional uncertainty of Q, is equal to the square root of delta x squared over x naught squared plus delta y squared over y naught squared. And you might notice that suspiciously this looks, well, this is the same result for the uncertainty for a product. So the, so the fractional uncertainty of a quotient is the same thing as the fractional uncertainty of a product. Okay, let's look at one final example. And this is an example that Wessel gives in his book. It's example 2.3. And here he looks at the equation for the acceleration of gravity in terms of rocking the moment arm L of a rocking pendulum and the period of the rock in the pendulum. So that's the length. L is the length of a pendulum, and T is the period. You may remember this from your physics class as a way to estimate the acceleration of gravity. So let's say that we are given that L is measured to be 92.95 plus and minus 0.10 centimeters. And the period is measured to be 1.936 plus and minus 0.004 seconds. So let's estimate G. So first, let's estimate the uncertainty of G. So the squared uncertainty of G is again equal to the partial derivative of G with respect to L times L and that whole thing times L, and that whole thing is squared, plus the partial derivative of G with respect to T times delta T, and that's all squared. And this becomes 4 pi squared over T0 squared times delta L squared, and I'm noticing I wrote L here. I should write delta L there. Delta L. Okay, so I wrote out the first term, and then the second term is minus 8 pi squared over T naught cubed times L naught times delta T. And again, we're tossing out the nonlinear terms of the uncertainties. And so that gave us delta G squared. The fractional uncertainty, delta G over G naught, and both of those are squared, is just, well, delta G squared over 4 pi squared L naught over T naught, and that whole thing is squared. And that turns out to be delta L squared over L naught squared plus 2 times delta T over T naught squared. And if we plug in our numbers, we get that delta G over G naught is equal to the square root of these two of the sum of these two terms here. And in this case, delta L was 0.10 centimeters, and L naught was 92.95. And then the second term is 2 times 0.004 all over 1.936. And these are in seconds. The first two numbers were in centimeters. And the answer is 4 times 10 to the minus 3. And I'll emphasize that I report that in one significant figure because the minimum number of significant figures that I know my uncertainty is given by the uncertainty in T. 0.004 is one significant figure. So I would write my answer for G, my estimate for G, as G sub naught plus and minus the uncertainty of G, which would be this fractional uncertainty times G naught. And the answer is 9.790. So I plug in all my numbers, and the answer I get is 9.790 plus and minus 0.004 meters per second squared. And you'll note, you should notice that I wrote my most likely value, the value made from the measured values of L and T, in terms of uh, in the thousandth place, which is the same order of the uncertainty. And so the last point I'd like to make, and we've applied this already to one of our examples, is if we have n independent variables controlling our function, or in our function. And so we would write the squared uncertainty of f, which again is the variance of f. And one short way to write that is the sum for I is equal to 1 to n of the partial f with respect to x sub I squared times the variance of x sub I. And you should refer to, this is the same as equation 2.37 on page 18 of Wessel's book. Okay, so that about does it for computing uncertainties of functions. You'll get to practice and hone your skills more in your homework.